that it does correctly what it's supposed to do. It's undecilable. Okay. So how can we do that? So there was a guy, which is Bloom, who was also a cryptographer, by the way, and who thought about something really nice. Is that imagine that you have a buggy program. Okay, imagine that you have a buggy program and we will self-correct it. That means that we will consider it as a black box and we will turn it into a correct program without doing anything to the code. Okay? So what is a buggy program? So consider, for instance, a buggy program that does the addition of two numbers. Okay? So the addition of two numbers, x and y, and it computes the addition. But you know that it's buggy on some instances. For instance, you know that it's buggy on p% of the instances, where p, I don't know, it's about 5. Okay? There are 5% of the instances but where the result will be wrong. Okay? But you don't know where, else you would be able to correct it. Okay? So you know that there are some region here where for some value of x and y, the result will be wrong. But you don't know where it is, it's the bug. Okay? How can I get a program that does the correct answer? So the idea is to use randomness. And in the following way. What you do is to draw two random numbers, r and s. Okay, so imagine that the addition is performed modulo something. Okay, modulo the sense. So what you will do is you have your additioner a here, that is buggy. And instead of computing a of x and y, what you will output is a of x and r plus a of y and s minus a of okay, yeah, this is stupid with addition. I should do it with multiplication. Anyway, imagine that we can do that correctly. Okay, assume that we can do that correctly. Okay, so imagine that it's well, it's because it's easier to do it. Okay, it's just to show you the concept. Okay, just to show you the concept. In that case, it won't work because here it's we don't know how to do it correctly. Okay. Anyway, assume that we can do that correctly. Okay. So what's the output here? The output, if all the computations were correct, the output would be x plus r plus y plus s minus r plus s. It's x plus y. Okay. So if everything goes right here, give the right result, we get the right result. So now what's the probability that everything goes right? The probability that everything goes right, yeah, it really doesn't work here. Anyway, let's, no, it's, but that's easy to explain. It's, because multiplication is much harder. It has huge form. Anyway, the idea is that here you have random input here. Yes, here you have a random input. Well, usually what you would like is that it's random over all the whole square. So let's assume it's random over the whole square. Okay, this is not the case here because I wanted to do something simple, but it's so simple it's wrong. Okay. So let's assume it's uniform. What's the probability that it fails? It's p. It will fail with probability p. Here it will fail with probability p. Here it will fail with probability p. This one is uniformly random everywhere. For this one it works. Okay. For this one it will give you answer only with probability. Okay. So basically, what's the upper bound on the fact that this whole process will fail? It's 3p. Okay. And now with probability at least 1 minus 3p, it will give the right answer on any input x and y. Okay, so this is true. This will be correct with probability 1 minus 3p for every pair of x and y, even the one that were buggy before. Okay, so basically what has done Bloom is to spread the bug everywhere. Okay, but not too much. Okay, so this is a really nice idea. I mean, it's you just correct the program by itself by just adding something which is just a trick afterwards. Okay, and you can even check the result. I mean that you can do some, you know, the proof by 9. You know, you sum up the numbers and everything, so you can generalize this idea and check that the result is correct, and just to reinforce this probability. Okay? So this is a very nice idea. It's the idea that you can correct a program without knowing anything about the program. You're just knowing that is what it's supposed to do. Okay? So even more surprising is zero knowledge stuff. Zero knowledge stuff is a very surprising idea. Is that, you know, when you have a credit card, okay, and you want to draw cash, you go to the machine, you enter the credit card, and you enter your PIN code. Okay? There is a problem here. At some point, the machine has, at the same time, your card and the PIN code. Okay, so you gave it everything. Okay, he knows everything about it, and he can do whatever he wants, and that's exactly what you know. There are cheaters that just put some specific device that read what the card as it goes, and that's exactly what you do. Okay, they can afterwards pirate your bank account without any problem. Okay, so the ideal thing would be to convince the machine that I know the PIN code without giving it, or without giving any hint about it. And it turns out that it is possible. Modulo some conjectures in computer science, again. And a very simple idea, explanation of that is, for instance, I want to convince you that I know how to count the leaves in a tree. Of course, nobody knows that. Okay, that's my secret. That's how you can recognize me. You know that I'm the guy who knows how to count the leaves of a tree. How would you do it? So I don't want to reveal my secret, and you cannot do it because you don't know it. You don't know how to do that. So what you do is very simple. You give me a random tree, okay, and you ask me how many leaves are there. I tell you, I don't know, 1,375,000. You have no way to check it. Okay, so what you do is when you ask me to close my eyes, and you remove a small number of leaves, but random numbers of leaves. Okay, and you ask me again to count the number of leaves in the tree. And then I give you another number. Okay? Now it's really easy to check whether I know how to count the leaves of a tree. You just do the difference, and you know whether it matches. If it matches, then you can reasonably assume that I know how to count the leaves of a tree. But if it doesn't, you know that I don't. Okay? Well, how to make sure that you didn't learn anything from that? Is that because you may have learned the number of leaves at the end. But no, because I added before a random number to the number I computed. Okay, and the same number, random number the two times. So, in this protocol, I've convinced you that I know how to count the leaves, number of leaves of a tree, without giving you any information, absolutely nothing. You don't know nothing, except that I know, with reasonable probability, that I know that how to count the number of leaves. Okay? So you can do much more sophisticated protocols like that, and this is quite surprising what you can do with randomness. It's kind of funny stuff. But you can convince somebody that you know something without revealing anything. Okay? So, by the way, how do you prove that you did not reveal anything? This is done by simulation. That means that you show that you can just remove the user and remove the guy that knows it and give the same sequence of, well, it's complicated. Anyway, so the other thing that I wanted to tell you about is the contribution to foundation. So this is why I'm here, is because I believe that computer science can help founding the complex system field, domain, to make it a complex system science. So as I showed you, whoops, that's interesting. Oops. Is defining what complex means. So that's still an ongoing issue. I'm not sure that we have a good idea about what it is, and I really believe that the contribution of cryptography might help. Okay, so thank you, and you might need that. So, any questions? No? Okay. Nobody understood nothing. Okay.